Okay, yesterday we started to talk about the need for modeling power converter in order to design the controller, the block that always is present in a power converter that is able to regulate the output by setting specific control signals at the input of the power converter. In order to do that, we need to perform two specific actions. Okay, the first one is to, let's say, averaging the waveform inside the converter. And the second one is the need for linearize it. These needs comes from the fact that any switch mode power converter is a variable structure system, is a system which is time variant due to the presence of switches inside the power converter, and then the circuit is intrinsically nonlinear. So we have a nonlinear time variant circuit, but our effort is directed to derive a linear time invariant circuit in order to, say, apply all the methods that typically can be employed in linear circuits and time invariant circuits. For example, I don't know, superposition effect holds in these systems. We can apply, for example, Laplace transformation. And so it's much easier to, let's say, have some, let's say, results, have some analysis, and basically it's easier to design a control system. Of course, in doing this kind of transformation, something is lost. Basically, are lost any kind of information which is related to the behavior of the waveforms of the converter inside each switching period. But this is not a problem because this kind of information can be studied, can be analyzed for steady state condition as we did before. Okay, so we don't have any more information about the peak value, about the root mean square value of currents. Okay, this can be done, say, just focusing on steady state. But now we are talking about dynamic situations, something which is no more cyclostationary conditions. The variables, say, have transients. And because in that specific situation, that a controller, say, have a meaning, okay? We lost also high frequency behavior of this waveform because the modeling techniques, the averaging techniques that we can apply only make possible to analyze frequency of variations of this waveform up to, let's say, half the value of the switching frequency, okay, since the Nyquist theorem holds. So there are certain, say, approximation. We neglect something that is not, say, is small in our, say, description, but in this way we can get a LTI system which can be more easy to study and to analyze. In order to perform these two steps that are averaging and then linearization, then a lot of modeling techniques have been developed since 70s of the last century. I'm just like to, say, talk about three of these methods, okay, that are indicated in the slide, that are the state space averaging method by Professor Middlebrook and Chuk, the same that, say, derived the converter topology. Remember the boost-back connection, okay, the Chuk. The switch averaging, Borperian, and the circuit averaging, okay, again, something by Middlebrook, okay. They were developed in different time, okay, so for example, the first one is the method that here is indicated as the last one, okay, the circuit averaging. Some of these methods are very formal in their mathematical expression, so they need to model a differential equation inside the converters and then provide a very detailed step-by-step description of the circuit. Mathematically heavy, for example, and other methods are, let's say, more circuital method. That means that I can apply this method basically directly on the circuit. Okay, so there are different views of the way I can derive, I can averaging and then linearization. I can linearize this converter. Okay, but basically they share the same goal. Okay, to obtain a linear time invariant, and to get this linear time invariant system, all the methods, not only the three that I say listed here, agree with the fact that you have first average equations, and then you have to linearize the system. Okay. Basically, all the methods provide the results in different forms. Okay, this is quite easy to understand. Okay, because the procedure they describe are different, each from the other. So also the results are expressed in different way, but basically the results are the same. Okay, if you look at what they said, okay, you can derive the same results for all. We can describe the method exactly in this order. So today we can talk about the state space averaging method, and then in the next lecture we can see other methods. Okay, the state space averaging method is a very formal method. Is a mathematical, let's say, there is a lot of mathematics inside, because basically the state space averaging methods focus on the differential equation that you can derive from the analysis of the circuit. Okay, you can take your switch mode power converter, analyze the circuits in order to isolate differential equations. In this differential equation, the state variable are highlighted, and the state variable are always that specific electrical quantities that are related to the energy in reactive elements. So, for example, the voltage across a capacitance and currents flowing through an inductance, that are state variables. To describe the equations, differential equation, which say describe the evolution of this state variable. And if you are able to describe in the correct way these, say, set of equations, then for sure you can derive a solution. Okay, so this is the power of this method is that is, say, mathematically heavy, because you have a lot of equations and you have to analyze basically the systems during the states. So during the on, when the switch is closed, during the off, when the switch is open, derive the equation, write down the equation. Then you have a set of equations, but then when you have written the system, then for sure you can find a solution, and a solution is always, say, can be written when you have this kind of solution. But if you want to discuss the drawback of the system, a drawback is that since this method is mathematical based, it's a matrix based system, sometimes the physics that is under this is hidden in these equations sometimes is missing. Okay, so you don't see any physical, say, justification of what you're right. Okay, because you are just sees a lot of equations, and then you have to solve these equations. So sometimes the physical behavior, which is on the basis of this behavior, is lost. Okay, so means that you have to, say, sometimes justify what you are, the results, why they are in that specific forms. So of course you have a lot of mathematics, you lost the physics that is hidden under this mathematics, a lot of steps. So mathematical here, but is always, let's say, is the basic of all the methods, because they formal derive a solution. Okay, the state space refers to a canonical form of expression, the state variables of a system. Okay, it's something that I think that somewhere in some other course you already derived. Okay, if you have a say system, whatever it is, but in this system you have some state variable, then you can write down a set of equations like that are described here. Okay, in which you have as x a vector of the state variable. I don't know, inductance, current, or voltage across capacitance. And you have the time derivative of these state variables. K, A, and B are matrices. Okay, K includes the value of the reactive elements, L, C. If you have mutual inductance, okay, you can put there. U is the input vector, so it includes all the quantity that you can say consider as input in your system. While, for example, Y here is the vector that includes the output of your system. Okay. For example, as an input in your system, you can put the input voltage. Okay. As output of your system, you can have, for example, the output voltage. Okay. But depending on your description, you can see a variable as input or as output, depending on what you want to derive. Okay. A and B are matrices that typically are simply, let's say, constants of proportionality between state variable vector and input and output vector. This is a formal description of this kind of state space averaging method. From my point of view, I find that describing mathematically this method is something that is not useful at all. So I want to describe this method by giving you an example of application. Okay, so let's apply the state space averaging method for a specific case that you want to analyze. For example, the case I want to analyze is the boost converter operated in CCM. Remember that I said several times during the previous lectures that no way to use the boost in CCM. It's difficult to control. It has a zero in the right half plane. So pay attention because, let's say, it's difficult to stabilize, to regulate the output voltage. Okay, let me show how it happens, how this right half plane comes out, and then we can apply the state space averaging method to derive, let's say, the description of the dynamic description of the boost converter. Okay, in order to do that, let me share the whiteboard. Okay. Okay, here you have the boost in the boost circuit. So we have the inductance and the switch and the diode in that specific the relative position. Suppose that this boost is during the time interval t on, and during t on the switch is on. And if the switch is on, the diode is off. So rewrite the circuit when the switch is on and the diode is off. Let me highlight the state variable of this system, that are the current through the inductance and the voltage across the capacitance, VC0. Look that in that circuit, the output voltage V0 is the same of the state variable VC0, the voltage across the capacitance. Okay, so we can use VC0 or V0 in our description. They are the same. Okay, this is what happened during the time interval t on. The switch is on, it's closed, and the diode is off, is open. So let me describe the state the vector of the state variable. Okay, this vector is IL, and then you have VC naught. The input voltage V in, for example, for us can be, say, the input vector. So this is the input vector. State variable vector. Okay, so let me write down the differential equation of this system using these definitions of the state variable vector and the input vector. Okay, how can you derive the state variable, the differential equation of this system? Simply write down the equations, for example, of the current and the voltage across these reactive elements, the inductance and the capacitance. Let me draw here a voltage VL, the voltage across the inductance. This voltage VL is the voltage V in, and this is L, the IL over the T. Let me consider this node, which you have IC naught, the current through the capacitor, the output capacitor C naught, and this is I naught. As you can see here, I C naught is minus I naught, which is minus V naught over R. But I C naught is C naught time derivative of V naught. So we derived these two equations that completely define the time evolution, okay, of the state variable in our system. Okay, so let me use the previous and formal description of the state variables that are in this way. L, let me rewrite the equation here. Okay, these are the two equations we previously derived. We can write in a matrix form, and the matrix forms is something like this: L, 0, 0, and C. Sorry, this is C naught. And then we have the time derivative. Let me call the time derivative in this way: IL with a dot on the top of the variable, V naught or VC naught for me is the same. If you want, I can write here VC naught just to highlight the fact that this is the voltage across C naught, okay? So we have VC naught dot, so this means that you have the derivative. This is equal to what? Okay, here we have this is the metric that we call K. This is the vector of the state variable. This is the matrix A, okay? This matrix A is IL, and then we have X. This is X time derivative, and this is X. X is IL and VC naught. And so, if you look at this expression, IL does not depend on any of these two variables here because it's equal to V in. Okay? While the voltage, the time derivative of the voltage across the capacitor is equal to minus V naught, or if you want VC naught, which is the same, over R. So it is 0 minus 1 over r. Then we have another terms here. Let me change the page. LC not IL derivative VC not 0, 0, 0, negative 1 over r IL VC not. Okay, quindi, so we have K, X, this is the matrix A, this is the state variable vector plus, then we have the matrix B, and then we have our input vector is just V in. Okay, so IL depends on V in because the IL on the T multiplied L is equal to V in. Okay, so we have here 1. And then you have a 0. Okay, so the matrix representation, what you previously derived, basically looking at the circuits, is written here. Okay. Now the vector, the B is not a matrix because we have just one input element in the U vector, so this is not a matrix, but is again a vector. This is what happened during T on. So this is for T on. Let me write this clearly here. So during T on means when the switch is on and the diode is off. Now, what happens when we have T off? So this is, we are in CCM, so we have no idle time interval T3, we have just T on and T off. And so when we have T off, we have to rewrite these circuits. Now the switch is off, so it's an open circuit, the diode is on. V naught, V in state variable are IL and VC naught, which is the same of V naught. Again, write down the differential equation involving the evolution of the state variable IL and VC naught. So again, let me have a look at the voltage across the inductance, and this is VL, which is L the IL over the T, and this voltage now is V in minus V C naught, or V naught is the same. What about the voltage across the, the current flowing to the capacitance? IC naught is C naught, the V C naught over the T, and this is now a difference between two currents because now we have the output node which is connected not just to the I naught current but also to the IL. So this is IL T minus V naught over R. So we have again a set of differential equations describing the system, and then we can express again, like before, these systems in a matrix form. So let me write down this matrix form. Then you have L, 0, 0, and C naught. Then you have, and this is the matrix K. Then you have this time derivative of the state variable, IL and VC naught. Now we have that IL depends on VC naught, which is a state variable. So you have 0 and -1. While VC naught depends on IL and VC naught. It's 1 and -1/r. Then you have the input variable Vin, and so you have just a vector, and Vin appears just in the inductance equations. So it is 1, and then you have 0. Okay? This is B, and this is U. Okay, so this happens during T off. So we have two different description of the boost converter. Of course, you can do the same steps for any other kind of converters. Okay, you have to say separate the variable structure system into say time domain into the domains in which you have a not variable systems. Okay, for example, during T on there is nothing that changes. Okay, because the switch is on and the diode is off, but then it happens during T off. So I divided the time variant system into time domains in which you have no variation of these switches. Let me rewrite these two equations simply by dividing the first part by the matrix K in order to have, say, in the left side of the equation, just the time derivative of the state variable X. Okay, so in order to do that, during T on, in which we have these equations here, we can write down that the state variable is IL time derivative, VC naught time derivative, which is equal to what? Then you have to say, basically you have matrix, say, division, A divided by K. This simply means that you have, here you have at the first row 0 and 0, and then nothing changes. Okay, 0 and 0. Then you have another 0 here, but then you have -1/r, and this becomes 1/r C naught. Then you have IL, VC naught as state variable, plus here you have 1 and 0, and that means that since you have to divide by the matrix K, this becomes 1/L, 0, and then this is V in. Okay, so we have the state variable time derivative, which is equal to a matrix that we can call A prime, that multiplies the state variable vector plus B prime that multiplies the input vector U. Okay, so we simply say have an expression in which on the left side of this equation we have just the state variable. Okay, it's just a arithmetical, say, manipulation. This during T on, the same during T off. Time derivative of the state variable, which is equal to what? Now the matrix A is this one, okay, is 0, -1, 1, 0, -1, 1, -1/r. Then we have to divide by K, and this becomes 0, -1/L, 1 over C naught negative 1 over R C naught. And this is IL, and this is VC naught. Plus the same as before, because the B matrix is always 1, 0. Okay, so you have let me modify a little bit this expression. This is, since we have two different time domains, T on and T off, let me call this matrix A1 and this is B1, okay? Because otherwise it seems that A are the same into two different, say, descriptions. So you have for T off A2 and B2, okay? So this is A1 prime, B1 prime, and then you have A2 prime multiplying X plus B2 prime multiplying Q. So 1 refers to T on and 2 refers to T off. Okay, so we derive these two matrix and compact description of what the state variable describe in the system. Okay. Are there any problems in this description? Okay. Simply say, looking at your system, divide your variable structure system into time domains which you have no variation of the switch, and this is typically T on and T off. Of course, you have to analyze the DCM. We have a third state which is T idle. Okay. And for any of these kind of description, which you have no variation of the switch, you can write down the state space equations. So the equations that describe the evolution in time of the state variable, okay, current through the inductor and voltage across the capacitors. So now remember that, and now I have to share again my whiteboard. Remember that we have to implement two steps, which the first one is averaging, and the second one is the linearization of the equations. So what does it mean, averaging? We have two different set of equations that are expressed here in terms of matrices, so matrix equations, that lasts, the first one during the time interval T on. So during the time interval in which you have to do the cycle D. So D, say, Ts, okay? So T on is equal to D Ts, where D is the duty cycle and Ts is the switching frequency. And the second one lasts for T off, which is, let's say, 1 minus D multiply Ts. What does it mean averaging, which is the first step, these equations? Averaging means that I can rewrite the two equations that are separated, say, matrices equations, into just one equation, taking into account the time interval in which the single equations apply. Let me write down, because it's simplest to write that describing by words. I just want to have a single equation describing what happens during Ts, not just T on and T off. So in order to do that, I know that the first equation, that during T off, lasts for dTs. The second equation, that is written in this whiteboard here, lasts in the time interval 1 minus D multiplying Ts. So why I cannot have something like this? A1 multiplying let's say A1 plus, sorry, A1 X, let me write down this way. Plus B1 Q. This is a first equation during T off, sorry, during T on. So this equation lasts for, let's say, the time interval, which is ts. But then we have to average over ts, so we can say that dts, and then we can derive averaging over ts in this way, plus a2, the matrix during t of x, plus b2 prime, which lasts for 1 minus dts. Okay, so basically I can cancel out ts. What happens is that I have the first one multiplied by d, and the second one, which is multiplied by 1 minus d. This is a definition of an average. Okay, I have that simply to understand that the first equation applies during dts, and the second one for, say, 1 minus ts. So this is during t on, and this is during t off. And ts is the summation of t on and t off. So basically, I have this description. Let me collect the A matrices together. For example, here you have A1, and then we have A2 prime. So let me collect A1 prime that multiplies D plus A2 prime that multiplies 1 minus D. And this is multiplied by the state vector. Then collect the B matrices, B1 prime D plus B2 1 minus D. That multiplies the input vector. Okay, so this is the new expression of the quantity x, the state variables, time derivative of the state variable, that can be considered to be the average description of what happens in my systems. Okay, so it's better now that we look at this equation and to let's see if this if it is reasonable, has a meaning or not. Okay, in order to do that, forget for just a few minutes this say matrix description, and consider a just one-dimensional situation, say scalar situation. Suppose that you have a variable which is something like this. A is a constant that can be described in this way. Okay, the situation is very similar to that I described up to now, but the difference is that we have scalar elements, so just one element, no matrices, and before we have say a matrices that matrix systems. Okay, so supposing that this is the equation, the scalar equation. So let's suppose a scalar systems like this. The solution of this differential equation, you should know that this is xt, x0, which is the initial condition, and then you have the exponential of at. So first of all, we have to say that the terms a here appears as an exponential part, and a is something which is the reciprocal of a time constant. Okay, so by taking a parallel, we can say that, for example, this part here, okay, and also this part here are, say, reciprocal of the time constant of our power converter. Okay, so this is just for, say, starting our description. Now, suppose that this is what happens, say, as a solution. So suppose that I have this system, scalar system, that has xt, which is equal to A1 xt, and this kind of description is true during the time interval dts. Exactly what happens in our description for the boost. And then we have this description, A2 xt, for the time interval 1 minus d multiplied ts. So, as happens for my matrix description, now we have a scalar system which we have two time intervals in which the equation, the state variable equation, let's say, are different. Okay, then we have two different constants, a1 and a2. Okay, I know that the solution is given by what I written here of this kind of solution. Okay, so we can solve this. Okay, this solution is scalar. Can we solve, say, much easier? Okay, what we written in terms of matrices before. I put as average quantities the expression that you can see in this whiteboard. I multiplied by d on 1 minus d the matrix expressions, and I put together, say, waiting for the time interval which they apply. So my question is that, is it true that the solution of this system, scalar system, is something that can be described in the same way? So I can write down that x variable time derivative is a1 multiplied d plus a2 multiplies 1 minus d, say, ts multiply x, sorry, x, ts is no more here. Okay, because this is what I'm, say, what I said before for the boost converter. I said that my solution for the system is just average quantities derived by weighting, say, the t-on state variable by d and weighting the t-off state variable by 1 minus d. So let me, say, analyze a more suitable, more, say, easy system, which is the scalar system, and let derive the solution. The solution is this one, according to our previous description. So let me analyze this for DTS. Let me solve this system mathematically. Can be done, taking into account that the solution was previously given. So, for example, at the end of the time interval x dts, we can have x dts, which is simply the initial condition multiplying a exponential of a1 dts. Okay, according to my, say, solution that I provided here. Okay, when t is equal dts, then you can have this solution. What happens to x ts, so x at the end of the switching period? X at the end of the switching period will be x dts, which is the initial condition for this second equation, and then I have a2, and this lasts for 1 minus d ts. X dts now is given by this expression here. So I can replace, and I can find that x at the end of the period is simply x0 exponential a1 dts a2 1 minus d ts. So it is x0 exponential of a1 d plus a2 1 minus d ts. This is x ts. So if you look at this expression, now you can describe this, say, solution in a differential form. So you can, say, take this expression and you can say that this is simply a1 d plus a2 1 minus d xct. So if you solve this equation, okay, in which you have the average quantities over d and over 1 minus d, you solve this equation, you can get this one. Okay, so for scalar system, this is true. For scalar system, the solution of a, let's say, variable structure in which you have, let's say, two different behavior during d and during 1 minus d can be described by taking the solution of the average quantities. This is the average. But there is a step here which is not true for matrix. When we have, let's say, look at this step here. We have that a exponential of a1 d ts multiply a2 1 minus d ts is equal to, say, exponential of a1 d plus a2 1 minus d. Yes. This is true for scalar, but this is not true for matrix. For matrices, this is not true. I cannot do, let's say, I can write down the same, say, expression when you have in place of a1 small cap and a2 you have the matrix a1, etc. So it seems that this cannot be, the solution is wrong. So I cannot write down my equation, my average equation exactly in this form. This can simply, say, done for scalar variable. When you have scalar variable, this is mathematically exact. When you have matrices, this is not correct. Okay, this is not correct because they do not, let's say, follow these rules. Okay, you cannot have this. So let me show an approximation by which I can say that the solution is good enough. Okay, so in order to understand how we can accept this average solution, let me rewrite the two exponential terms now matrices. Okay, so I replace my small a1 and a2 with say, the capital letter, now our matrices, and a2 1 minus d ts, and a first order approximation can be done by expanding these matrices. How can we can expand an expansion of this matrix exponential is done by taking the form in which you have the identity matrix, then you have a1 ds plus 1f of a1 square value d square ts square plus all other orders. Okay, so you can expand in this way the exponential of a matrix. The same you can do for this other matrix, a2 1 minus d ds plus 1f a2 1 minus d square ds square plus etc. etc. Now let's have a look to the a1 d ds. Yes, a1d plus a2 1 minus d ts. So the exponential in which the exponent part is the average quantity. Okay, this can be done. It can be expanded in this way: identity plus, then you have A1 d ts plus A2 1 minus d ts plus A1 A2 d 1 minus d ts square plus etc. etc. Okay, so I expanded in this way the single exponential part of this matrix and the exponential of the average matrix description. Okay, so now we have to let's say understand that in this expansion there are some contributions that are very small. Okay, remember that as I said before, and this is a important consideration, that the part that in this exponential solution multiplies the time variable t acts like a quantities which is 1 over a time constant. Okay, always if you say describe the evolution of a system in a scalar way, a is 1 over constant. For example, in a say discharge of a capacitors, you can have a which is 1 over rc, etc. So the physical meaning of a is to say have some say relationship with the time constants of the circuits that kind of differential equation described. Okay, so if this is the meaning, so we have to consider that also in this case, the matrix case, the quantities that multiplies the time interval, so A1, A2, etc., are some relationship with the time constants of our systems. Okay, now the system is say is a matrix forms, but the physical meaning remain the same. Okay, so these matrices represent time constants of our circuits. What is the one of the basic assumptions that I always put, say, at the basis of my analysis, is that the time constants of the reactive elements in the switch mode power converter are much larger than the switching period Ts. Much larger than Ts. So in order to do, if you understand this fact, it means that, for example, this quantity here is negligible, okay, because it's the product of A1 and A2, and then you have Ts here. Okay, so you can approximate this quantity simply by neglecting these second order terms, because let's say this happens for microinstruction. Okay, the reactive elements have time constants, switch mode power converter, that are much larger than the period. So this approximation holds. This is identity matrix plus A1 dts. This is identity matrix plus A2 1 minus dts. And the summation here is average quantity is identity matrix plus A1 t ts plus A2 1 minus dts. Okay. If this let's say approximation is true, and this always happen in switch mode power converters, then we can say that exponential of A1 dts multiplied by the exponential of A2 matrix 1 minus dts is equal to what? But is roughly the product of these two expansions, simplified expansion. Okay, so it is identity matrix plus A1 D TS identity matrix plus A1 1 minus D TS. And if you get multiplications, then you can get identity matrix plus A1 D TS plus A2 1 minus D TS. Okay, but this expression here is exactly this one. So is the expansion of this quantity here. And so this is A1 D plus A2 1 minus D TS. Okay, so as you can see, this product of two exponential of matrices is given by this quantity, but this is just an approximation. But if you can do this, then the situation is similar to that of let's say scalar form, so in which you have this quantity here and this quantity here. Now this expression here now holds for matrices, for matrix description, only if, let's say, time constants is much larger than TS, as it happens in circuits, switch mode power series. So my description and my analysis is an approximated analysis. Okay, remember that we are averaging quantities, and in order to averaging these quantities, I can accept some, say, approximation. Okay, in order to neglect something which is not important in my dynamic analysis. Okay, in this case, I have to consider that the, say, time constant of my reactive elements should be much larger. Okay, this leads to a very small representation error. Okay, because this happens typically, but you have to be aware of this kind of approximation. So that means that my description here, in which my total states variable description is written in these terms, so averaging the state matrix description during D TS and during 1 minus DTS is good enough. Okay, it's not exact, but you can say that is, say, as a certain approximation, but can be done. Okay, so we can describe in this way, and this is an average expression. Okay, you say taking the average of the two variable structure in two time domains in which you have no variation, you get the average description of the matrix equations, and then you can consider the final state variable differential equation as written by using the average quantity in this way. So as you can see, there is an approximation which is, say, not so bad, given that in our converter our assumption, which the time constant is larger than TS, typically is true. Okay, so you have questions about that description? As you can see, the mathematics that is, say, described in this way is, let's say, can be, say, heavy if you want. You have to describe mathematically this, and I'm talking about just a system in which each component is ideal. Okay, I have not inserted ESR, I haven't inserted RL, so in series with the resist, with the inductance, etc. Okay, if you insert this kind of parasitic, then the description is, let's say, much more difficult. Okay, then there are certain approximation that depends on the matrix description, etc. So at this point, you can see that there are a lot of maths. And another consideration that I made at the beginning is that some, say, physical description, some physical justification is not immediately evident. Okay, for example, my approximation that I just made that depends on the time constant is not physically evident, let's say, just looking at the equation. You have to make some reasoning to understand that I have to do with time constants of a circuit, that solution gives us that the matrix multiplied the duty cycle is, let's say, something which is related to the time constants of the reactive element. So there are some, let's say, difficulties in deriving this kind of equation. Okay, something that can be, let's say, skipped in other methods that we can solve next time. But let's continue, because we have just averaged the system, but we have no finished at all. We have now, as is though, let me again share the whiteboard. So we have this kind of description. Okay, now let me write down this matrix, okay, which is I1 prime D plus HU prime 1 minus D, B1 prime D plus B2 prime 1 minus D, to see what's inside, what are inside this expression. Okay, so in order to do that, let me rewrite A1 prime. A1 prime is 0, 0, 0, negative 1 over RC naught. Then I have A2 prime, and A2 prime is 0, negative 1 over L, 1 over C naught, negative 1 over RC naught. Then I have B1 prime, and B1 prime is 1 over L, and then we have 0. And B2 prime is 1 over L, they are the same. Okay, so my expression is that x t, the time derivative of the state variable, is A1 prime multiplying the duty cycle plus A2 prime multiplying 1 minus the duty cycle, x, plus B1 prime D plus B2 prime 1 minus D U. Okay, so I want to see the expression of these two matrices, the red one and the purple one. Okay, the red one is given by A1 prime multiplying D plus A2 prime that multiplies 1 minus D. So let me write here. Then you have A1 prime multiplying D. So it means that you have 0, 0, 0, negative R as 0 multiplying D plus 0, negative 1 over L, 1 over C naught, negative 1 over R C naught. That multiplies 1 minus D. Okay? So this becomes, this is 0. Then you have a negative 1 minus D over L, 1 minus D over C naught, negative 1 over R C naught. Okay, so this is the matrix here. Let me read. What happens to the B average matrix. The B average matrix is given by is 1 over L that multiplies D plus, this is simple because it's 1 over L, 1 minus D. So this is simply 1 over L. Okay, this is the purple matrix here. Okay, so our average differential equation can be written in this way. 0, negative 1 minus D L, 1 minus D C naught, negative 1 over R C naught, that multiply IL, let me write X, plus 1 over L 0 of U. Okay, this is my average description of the system, so something that is not equal. So if you want, we have an approximation, but anyway, we can use it for the next step. Okay, let me say something about the duty cycle D. Okay, I here put the capital letter D, and this is always done when you have something which is constant. You have a DC quantity. Okay, remember my definition of, let's say, average value. Okay, I always use capital letter. Okay, this is something that is constant. Typically now that we are facing something which is variable, we are in dynamic description of a system, then there is no variable which is constant. We have to consider duty cycle, which is something that can vary. Okay, we can include the input voltage V in, which is not constant. It can vary. And the output voltage is not, say, something which is constant by definition. We have to regulate it. The current, output current I naught, is not constant at all. So we are facing a situation in which you have to say something about how the system reacts to variation and disturbances. Okay, so there is no reason to put here D as let's say a capital letter. Okay, this is because D now is something that varies. Okay, with the time, like the V input, the V naught voltage, etc. So I refer to these quantities with using the small letters. Okay, so D is something that changes, if not more a DC quantity. So let me redraw the letter D here with something which is small. Okay, and I put also the T variable to say stress the fact that now the duty cycle changes with time. Okay, this is important for our, say, further steps. Okay, so as I said, now we have an equation which is the average expression of my dynamic system, in this case the boost. The next step is to linearize it, okay, because the system is not linear. It's not linear due to the fact that you have, for example, the duty cycle that changes with time. All the variable here changes with time. The input voltage, which is included here, okay, changes with time, but also the state variable are changing, okay, are included in the state variable system. The duty cycle is changing. So the system is, let's say, time invariant, because we have averaged, but is not linear. Okay, so we have, for example, that the current IL is not constant. The current IL changes. Current through inductance, the state variable. And so we can describe it separating a contribution in the IL, which is constant, to a contribution that is just variable. So we can separate each of these time variant, let's say, quantities into a DC component and to an AC component. So in other words, we can write down IL capital letter, meaning that this is a DC quantity, plus something which is, let's say, variable. Let me draw in this way. We have this cap over the variable. Say that this is just an AC quantity. Okay, this is AC quantity, and this is DC quantity. The same for the duty cycle. Duty cycle changes with D, but then we can recognize that the duty cycle changes on the basis of a DC quantities, and then you have a variation. And then you have V in that as a V in DC quantities plus a variation, okay? And also for VC naught. VC naught as a quantity which is, say, constant, DC contribution, and a quantity that can be variable. So we can think about all these, say, time variable quantities by considering that you have a, say, DC quantity, this is contribution that is constant, plus superimpose on it a, say, AC variation. And this is the step, the first step in linearizing the circuit, okay? If you think about this kind of description, nothing changes respect to something that you already know. For example, in the diode example that I gave you yesterday, okay, I always, if you want to linearize the behavior of a diode versus small signal variation of the current through the diode, I have to think about of a DC operating point. Okay, I have to think about that the current is, say, is biased in a certain specific point, and then superimpose on this variation, I have a, say, AC variation. The same description is given here. Okay, I have a, let's say, operating point, which is given by the DC quantities, IL, D, V in, and VC naught, capital letters, plus small variation. Okay, small variation because in my analysis, if you want to linearize the system, I have to think about of small signal linearization. Means that the variation of the, for example, the AC contribution, always less than the DC contribution. This happens for all variables. The duty cycle AC contribution is, in my assumption, very much smaller than the, say, DC quantities. V in variation is much smaller than the DC quantities. VC naught AC contribution much smaller than DC quantities. Okay, this is my assumption, which is a small signal assumption. Okay, so my linearization, say, is based on, say, the consideration on the assumption that I am in presence of a small signal AC variation superimposed on a DC operating point. Okay, but this is nothing new to electronic students because it always happens in nonlinear circuits, nonlinear components when you want to linearize them. Let us have a little break, 10 minutes break, so we can say see at 10, 10, 5, 10, 3, 10, 3, 10, 5, okay? Have you any questions, remarks, comments on this, the state space averaging techniques, mathematical derivation? Is all clear enough? Something which is one favor that you can do to me is and to your own is to check my computation, okay? Because it's very easy to forget some say variable in deriving say final result. So please consider that I can make errors, but okay, if you help me, maybe I cannot say made mistakes. Okay, so okay, let's continue our say discussion. By the way, this topic, the topic which is included in the slide which has the number 7, modeling of power converted, is a topic that I could ask in examination only to students of electronics. Okay, students of mechatronics are welcome here to say see the lecture. They can download, no problem, but students of mechatronics will not be examined about the state space averaging technique, the circuit average, and the switch method. Okay, so this is what is given in the examination. Okay, let me continue our discussion. Okay, because now we are on the edge of, let's say, linearizing the time invariant system I just derived. Okay, so let me share again the whiteboard. And I have here an equation, okay, which is the average equation, state space equation. And here I have a small signal approximation. Okay, let me rewrite this matrix equation into, let's say, classical standard set of equation without no matrix at all. Okay, so xt, you have the I L over T in the T, which is equal to negative 1 minus D over L multiplying Vc naught. So it's negative 1 minus D T over L Vc naught over T. And then plus 1 over L V in of T. Okay, this is the first equation. The second one involves the Vc naught in the T, which is equal to negative 1 minus dc naught multiplied IL minus one minus d c naught IL d negative 1 over R C naught multiplying Vc naught. Negative 1 R C naught over T, and then stop. Okay, so the metric equation can be written in the standard way, in this way. Okay, see, these are my average system, okay, with that approximation that is related to the time constants of the reactive elements. But then we have this small signal, the description. Okay, each variables, it includes an AC part plus a DC part. This variable, this one, and also this one. Okay, and then we can separate, we can describe in two different ways. So let me replace this kind of description into this matrix in this, sorry, there is no more matrix, this, say, differential equations. Okay, so I have the d of IL DC plus IL AC over the t is equal to negative 1 minus d minus d over L Vc naught dc, Vc naught AC variable, plus 1 over L V in capital letter plus V in AC. Okay, just replacing my description of each variable in terms of DC and AC contribution. The same for Vc naught, which is equal to 1 minus D minus DAC, C naught, IL capital letter IL AC variation, 1 over R C naught V C naught plus V C naught. Okay? Let me check. Is okay. Okay, good. So as you can see here in these differential equations, we have DC parts and AC small signal parts. Okay, the quantities with the hat on them. So let's separate the DC quantities from the small signal AC quantity. Okay, so DC and AC parts. Let's start with the DC. So it means that I can separate. There is no difficulties in doing that. It means that I have the IR over the T, which is equal to 1 minus D over L VC naught plus 1 over L V in. Okay, so I jump not considering the variable with the hat on them. Okay, just considering that say capital letters. The same for the VC naught over the T, and this is 1 minus DC naught IL minus RC naught BC naught. Okay, this is the system for DC variable. Now, if you take the time derivative of a DC quantities, which is constant, of course you get 0. So these quantities are null. Okay, so let's solve, for example, the first one. Okay, remember that VC naught in my circuit now is the same as V naught. Topologically, the voltage across the output capacitor is exactly the output voltage V naught. So we can say that for the first one, for example, I have that D minus 1 now multiplying V naught plus V in is equal to 0. So that means that V naught over V in is equal to 1 over 1 minus D. Okay, maybe you recognize this expression. This expression is simply the conversion ratio in CCM of the boost converter, already derived from steady state analysis. But when you, let's say, consider only the DC quantities in our, say, differential expression, then we are assuming that you are in the steady state condition, which you have no variation of the variable. Okay, you have no small signal variation. You have just all the variables that are, say, in their final steady state conditions. Okay, and so this means that we go back to our cyclostationary steady state analysis, and then we can, for sure, have the same results. And this is the proof and validate my hypothesis. Okay, this in DC, then we get this kind of solution. From the second one, for example, you can consider here the second one, and from the second one you have 1 minus D IL minus V naught over R, which is equal to 0. So that means that IL, DC quantity, is equal to V naught over R, 1 over 1 minus D. But this is not surprising at all, because what is IL DC quantity? IL capital letter. IL capital letter, let me show these directly on the circuit. Okay, if you look where it is. Okay, good. If you look at the boost, okay, IL is here. Okay, IL average value is the input current. Okay, IL average value is the input current in steady state in DC, because no current can flow through the input capacitor in steady state. It's okay, and so we have that IL capital letter, this quantity is the same of the input current. Okay, here, so this is I in, while V naught over R is I naught. So we just get this equation. I in is equal to I naught 1 over 1 minus D. And this is M, this quantity. But this is correct. We know that in lossless systems, okay, the ratio between the output voltage and the input voltage is the conversion ratio, but the ratio between the input current and the output current is the conversion ratio. Okay, so this is good. Okay, we verified that something that we already know from the steady state analysis. Okay, of course, this is not our goal here. Our goal is to investigate something into the small signal behavior. So let's consider the AC contribution. Okay, we get the DC, and now analyze the AC part. So let me say analyze the circuits in terms of AC quantities. Okay, so in terms of AC quantity means that I have to rewrite these equations here, taking into account the contribution of the small signal variable. Okay, so it's not so simple as in the DC quantity. Okay, DC quantity simply I skipped all the variable with the hat on them, and then I get the DC quantity. Here is better to have all the variables multiplied because there are some multiplications, and then at the end remove the DC contribution. Okay, for sure I can say that in this part, in the left hand of this equation, I can skip the DC contribution. Okay, so I can have here the IL over the T. This is correct, but in the right hand of this equation, let me do all the multiplication. Then just only at the end I can eliminate the DC contribution. Okay, because there are something can be analyzed again. So we have 1 over L that multiplies this expression to VC naught. Okay, so let me write for my, let me write in this way. So changing the sign, so skipping the negative sign at the L, and this is VC naught plus VC naught at plus 1 over L V in plus V in hat. Okay. I changed the sign here just to say not having the minus. This is 1 over L. Then I have VC naught capital that multiplies D plus VC naught that multiplied D hot minus VC naught. Okay, I multiplied the first one to these parentheses. The same with the other. So D VC naught hat plus D VC naught minus VC naught hat plus 1 over L. This is simple because this is V in plus V in. Okay, so now I have to skip the DC term. Let me show you that this is a total DC term. This is the total DC term. I just want to say retain the AC contribution. Okay, As you can see here, there are terms that are not completely DC. Okay, for example, this one is say something that is multiplied by a variable quantity, so I have to say include in my analysis. Okay, this is a DC term, and all other terms includes variation. Okay, this is the reason why I have not skipped say VCO say at the beginning of my the small signal quantities with the atom and with the capital letter, sorry, at the beginning of my analysis. Okay, because otherwise I lose some of this contribution in this sum. Okay, now look at what happens here. You have I skipped all the DC contribution, but I have contribution like this one, for example. Look at this contribution here. This is the product of two small signal terms. If I say assume that D is very small compared to the capital, let's say, DC quantities, and the same happens for BC naught. When you multiply two small quantities, okay, then you get a quantity which is well lower than each single small quantity. Okay, so this is a second order term. This second order term in a first approximation can be skipped. So I can say put this contribution to be null. Okay, and so with this hypothesis in which second order terms are negligible because they are very small compared to all the other variables to which this contribution is summed up, I can write that the IL hat is equal to 1 over L of V C naught D hat plus D capital V C naught minus V C naught plus 1 over L of V in hat. Okay? Do the same with the second equation. Okay? Let me write this equation, which is here, that naught over the T, which is 1 minus D over C naught IL plus IL hat minus 1 over R C naught V C naught plus V C naught. Okay, there are some terms that I can skip basically at the beginning, like this one. For all others, I have to perform multiplication. Okay, so I have 1 over C naught that multiply. Okay, IL for this parenthesis, IL minus ILD minus ILD hat plus IL minus ILD minus DIL out minus 1 over RC naught VC naught. Again, we have DC contributions that are this one. I can skip them now because I'm just looking for AC solution. And there are second order terms like this one. Okay, multiplication of small signal, second order term. And so I have the final expression, the VC naught over the T, which is 1 over C naught IL minus ILD minus ILD hat minus VC naught over RC naught. Okay, so we have these two equations, this one and the previous computed, which is this one. Now, in these two expressions, there are some contribution, for example, I don't know, IL here, that was, or maybe also VC naught here, that was computed in the previous DC analysis, okay? For example, here. Let me write here that VC naught, which is V naught, is the same, is V in 1 over 1 minus T. And then also we have that IL here is V naught over R 1 over 1 minus T. Okay, these quantities was derived from the DC analysis. So we can use this expression into these two equations. For example, I can say put the expression of V naught over there. Okay, let me do this computation here exactly in the same way I did in the slide. Okay, let me check. Okay, we can do now or we can do later. In the slide I put this step later. It's not important. This is good enough. It's correct to define now that we need this equation. Okay, but let me redraw these two equations for say my non-complicating too much what I'm saying here. So let me write down DIL here. So DIL hat over the T, which is equal to 1 over L. We put V naught, or VC naught is the same, D star D hat plus, then we have D minus 1 V naught hat plus V in hat over L. Let me see if this is correct. Yes, I put here VC naught and then I put D minus 1 here for these two, and that's correct. The same can apply here when I have IL 1 minus D for these two, and so I can write down the V naught, the T, which is 1 over C naught minus IL D plus 1 minus D IL. Negative V naught over R C naught. Okay. We can have these two equations now, and in which we can, say, replace, for example, here we have V naught and we have here IL, the quantity that previously we derived for the DC analysis. But this holds for AC small signal, okay? So this is my final model. This is the linear time invariant description of our system. We have two steps. The first one was averaging the differential equation. We get an approximation due to the fact that it is required that the time constant of the system should be well higher than the time switching period. And then we linearize these time invariant equations by taking as another approximation, which is a small signal approximation, with the variation of the quantity I'd like to study should be much smaller than their DC quantities, okay? This set of two differential equations now are linear time invariant equations, okay? And when you get linear time invariant equation, you can apply, for example, all the methods that typically can be applied for linear system. For example, you can use superposition principle. You can use Laplace transformation, okay? So let me analyze these two equations, okay? This set of equations, if you want, into the Laplace domain, okay? So in order to continue, let's rewrite equations that are linear and time invariant in Laplace domain. That means that the time derivative is simply written as S variable, and then I have IL S, which is 1 over L V naught Laplace domain requires always capital letter, okay, but I have put here the hat to let you know that this is the AC contribution, okay? And this is V naught press quantities. Okay, so we have this expression here, plus V in over S divided L. The same happens for the other equation, which is S V naught hat, which is 1 over C naught minus IL D hat plus 1 minus D IL hat S, and then you have V naught over R C naught. Okay, so I can use Laplace domain, and Laplace domain, the same equation can be rewritten this way. So you pay attention to not confuse this variable here with this one. This without the hat is the DC quantity. This with the hat variable is the Laplace transformation of the AC contribution. Okay, so now the discriminant is by the hat, by the capital, because by definition Laplace domain always have, maybe I in the slide that maybe this is not correct, because Laplace domain when you get S, always you have to put the capital letter. Okay, if you follow my reasoning, this can be clear. So this is the expression of the Laplace domain. Now we have to consider what is our goal. Okay, our goal is, for example, to describe my boost. Okay, in this case the boost, my say converter, in order to understand what happens, for example, to the output quantities when some of this variable changes. What I mean, for example, I want to analyze what happens when the output voltage changes against the variation, for example, of the input voltage. Okay, what happens when the input voltage changes? What is their, say, effect, their influence on the output voltage variation? Because remember that I have to design the controller. Okay, so I have to understand which is the, say, influence of any other, say, variable in the systems affecting the variation of the output voltage with the quantity I want to regulate. Okay, so this, of course, is something that is not, say, in steady state variation is not, let's say, so important, because I'm just looking at the situation which all the variables stable. Okay, in dynamic situation, this is something that I have to, say, analyze. So there are certain transfer functions, okay, that in a linear system are the ratio between, say, a variation and, say, the effect of this variation on the system that I have to analyze. One, for example, is this one, which is called GV in of S. Of course, this kind of transfer function have to be analyzed one at a time. So, for example, in my system, as I said before, there are many variables that can change their behavior. For example, I said that they can change the current IL. The duty cycle can change, the input voltage. The output voltage is something that I have to regulate. So I cannot evaluate the variation of the quantity that I have to regulate, so the output voltage, VC naught or V naught, including all the possible variation. Typically, what I can do in a linear system is to apply superposition. Now we can apply this kind of, say, theorem for linear system, because we applied two steps that for a linear, non-linear, and time-variant system make possible to get a linear time-variant system. So in that situation, it's possible to use some sort of theorem that would be useful. So in order to analyze how the voltage changes with respect to the variation of all these variables indicated here, I can evaluate by superposition process and principle the effect of each of this single variation when all other variations are, let's say, are null. For example, I can evaluate the effect of the input variation of the voltage on the output voltage VC naught by taking the variation of the duty cycle, for example, of the input current to be, say, null, because this is the superposition problem. I can evaluate the variation of the output voltage versus the variation of the duty cycle, which is very important, is the control quantities, when I consider not varying the input voltage. Okay, so this is possible now in a linear time invariant LTI system. Okay, this is the reason why when I look at this transfer function in a linear system, transfer function have meanings. I have to put here, for example, the variation of the duty cycle null, and all other variables that I can include in my analysis. Remember what this function is called, because we just met this kind of, say, transfer function. In steady-state analysis, anytime we had, say, our buck boost analyzed, both in CCM or in DCM, then at the end, I list some parameters that can be useful for the analysis of this converter. One of these was, for example, the V naught over the V in, which is called the audio susceptibility. So this is, again, the audio susceptibility, but this is the transfer function, while the audio susceptibility that we met in our, say, analysis in steady state is the DC quantity, the DC value of the audio susceptibility. Now we have the transfer function, so the, how can you say, the behavior of this transfer function frequency by frequency, because it happens it's a variable of a plus variable. So now I can extend my, say, concept of audio susceptibility, that here is for frequency which is null, so at DC. Now it's computed for all frequency, okay? This is the meaning of a transfer function, the variation of, say, a ratio versus the frequency. Okay, so I'm extending for this analysis the concept that some of the concepts I previously described, like, for example, the audio susceptibility, in a transfer function domain, so in Laplace domain, so looking for what happens for different frequencies. While previously in the steady state analysis, I evaluated these parameters just with frequency 0, because we are in steady state, okay? This is the audio susceptibility. What's most important in analysis in order to design the controller is how the duty cycle variation affects the output voltage. So it's important to understand which is the transfer function between the variation of the output voltage versus the variation of the duty cycle. Of course, by applying superposition problem, when, for example, the input variation is null. This is called, remember, the gain. we at DC evaluated the variation of the output voltage versus the duty cycle, and we call this parameter the gain. Now we have the transfer function of this gain, so I analyze what happens frequency by frequency, while in, say, steady-state analysis, we evaluated at frequency 0, so at DC. Now we can evaluate for different frequencies, okay? So, since the controller design is my goal, okay, makes sense to understand how the output voltage changes with respect to variation of the control quantity, the duty cycle, which is the quantity I put inside the converter to control the behavior to regulate the output voltage. So, as you can see here, this quantity is defined with the variation of the input voltage 0. So that means that my previous expression that is here, Laplace expression, I can put the V in variation to be 0. So I can skip this term here in order to evaluate that transfer function. Okay, if I want to evaluate the auto susceptibility, I have to put this duty cycle 0. Okay, so I have a totally different. So in order to evaluate transfer function, the gain, transfer function, V in S should be put to 0. Okay, and so I get that specific equations. So now there is a huge step, because I have this expression here, which I skipped V in, and then I have this quantity, the second equations. Okay, so let me redraw. Let me rewrite this equation, because otherwise I will be lost. Okay, I have S I L at, which is equal 1 over L V naught D at plus D minus 1 V naught S without V in contribution, because I'm searching for the gain transfer function, 1 over C naught minus negative IL D plus 1 minus D IL S minus 1 over RC naught P naught S. Okay? So, take this second expression here, and for example, when you get IL hat here, replace the first equation. Okay? It's a long process, but step by step we can do that. Okay? S V naught S is equal to, okay, let me, 1 minus D over C naught, 1 minus D over C naught, multiplying IL, and in place of IL I can write down the first equation. So it is V naught over SL, V naught over SL multiplying D at plus D minus 1 SL multiplying V naught, D minus 1 SL V naught, yes, minus IL over D and C naught, which is this contribution here, and then you have minus 1 over R C naught V naught over S. Okay. Now, at this point, okay, we can exploit the DC quantity here. Okay, I can use this expression, and when I use this expression, I can replace, for example, V naught here and IL here. So let me rewrite, check my step if I made error. 1 minus d C naught, then I have let me collect before to do this all the terms which you have d star, okay, and all the terms we have v naught star. Let me start with v naught star, star at v naught at, which is this one and this one. So it is d minus 1 over SL and then you have C naught, and then you have 1 minus d. The other one is negative 1 over R C naught, and stop. Then collect all the terms that includes the at. And the at are, say, this one and this one. So it is V naught SL C naught one minus d minus IL C naught. Okay, now replace IL here and replace V naught here. We can put a minus here, and then you have 1 minus d square. Okay. Then V naught is V in that multiply 1 over 1 minus d. So it is V in that multiply 1 minus d, and then you have SL C naught. But this is again multiplied by 1 minus d. IL is I in, so it is V naught over R C naught. Let me check for avoid error. Is V naught over R 1 over 1 minus d. Okay, then we have another step. This can be, say, eliminated. Then we have that V naught is again V in. So this term is V in 1 over d R C naught, and then we have another 1 over d here. So it is a square. Okay. So is almost at the end. We have S V naught of S, which is V naught that multiplies negative 1 minus d . SLC naught minus 1 RC naught. Then you have plus D that multiplies V in over SLC naught minus V in over y minus d square RC naught. Okay. As you can see here, we have as variable V naught and D. Okay, this is exactly the variable that are included in the transfer function, the gain I want to say evaluated. Okay, so let me, for example, multiplying both the side by SLC naught. So let me do this. Say, if I multiply SLC naught here and here, you get SLC naught, which is equal to V naught SLC naught divided by this one is given by 1 minus D. And you have here SL over R plus D V in minus SL V in over R 1 minus D square. Now we can take V naught from here to the first side, okay, just collecting all the terms, having V naught. Then we have S square L C naught plus 1 minus D square plus SL over R, which is equal to D hat. Then you have V in minus SL V in R 1 minus D square. Almost done. Okay, because now we have to simply divide V naught by D, V naught hat divided D hat. V naught over D hat star is V in minus SL V in over R1 minus D square over SLC naught S square plus 1 minus D square plus SL over R. A little manipulation, okay, we can collect, for example, V in from the numerator and 1 minus D square from the denominator. So we have 1 minus SL over R1 minus D square, and then denominator we have SLC naught over 1 minus D square plus SL R1 minus D square plus 1. Good. I made no error, no mistakes, seems to me. Okay. So what we can say about this expression? First of all, this is a transfer function. This is the transfer function that we can call the transfer function between the duty cycle and the output voltage. So VD stays exactly this concept. Of course, this quantity was computed by taking V in hat equal to 0. This is my gain. Now, this is a behavior in terms of frequency. But look what happens, for example, if S is equal to 0. What does it mean? S equal to 0 means that you are at frequency 0, so DC. At DC, this GVD, the S0 is exactly V in over 1 minus D squared. If you check now the slide about the boost CCM, this is exactly the gain that we computed in that situation. The gain already computed for the boost CCM. Okay? Now the expression is more complicated because now we have to take into account the variation with the frequency. Okay? And what about the variation with the frequency? Look at this transfer function. We have, okay, this is a constant term, okay, the gain at DC, already computed. Numerator, we have the 0, and the 0 is, let's say, F0, which is 1 minus D square R over 2PL. This is the 0. But then you have a minus here. What does it mean? That this is not a left half plane 0. This is a right half plane 0. We analyze the effect of this 0 later. Okay, the minus sign here is typical for right half plane 0. Okay, typically the good 0 have plus 1 plus S something. Then you have a denominator, and this denominator you can recognize two, say, poles. They are conjugate poles, and the poles have frequency that are 1 minus D square, no square, okay, because it's the square root of the coefficient of that square, so it is 1 over D 2P L C naught. L C naught. And then we have this parameter here, which is also called GVD0, because it's at frequency 0, okay? So we have a couple of conjugate poles, but look at what happens to this pole. The poles change with the duty cycle, and so these poles, let's say, have some, say, they are not fixed. They change depending on the duty cycle you are including, depending on your operating point. Then these poles are, say, changing their position. So typically, this fact is defined, indicated by saying that in this case they are moving poles. The 0, which is a right half plane 0, is again a moving 0 because it depends on, let's say, duty cycle, but depends on the load. They are moving 0. So we have a moving 0 and two complex conjugate moving poles. Okay. Have you some questions about this? How I derived, apart for, say, the mathematical, the computation that can be quite longer. Okay, but I think that should be what's important here is to understand the approximation. When I put the approximation, why I get that approximation, and what is the cost of having this kind of approximation. Okay, all my derivations are indicated here. This is what I derived. Okay, so I have, say, these expressions here in a standard form. These control function. This control function is called, typically it's called the gain when you look at the DC quantity, like we did for the steady state. When you have, say, the transfer function, say, so the variation versus frequency, this V naught over D transfer function is also called, somewhere you can find books and literature, control to output function, because it's exactly what is done. So this is control D duty cycle to the output V naught function. It's control to output function, or if you look at the gain at DC, the DC gain. In a standard form can be written also in this way, okay? In which you can, say, define also quality factor, which is, say, appears in the coefficient of the variable S, okay? So you can write down this expression. This happens for the boost, okay? So the boost has this right F-plane 0. So let me discuss a little bit the why this right F-plane 0 can be dangerous in the boost operation in CCM. In order to do that, look at the slide. This slide shows you a system, a very simple system, which is nothing to do with our converter. It's a totally different system, which is described by an output variable, which is U out, and then you have also an input quantity, which is U in, okay? And this system is so simple that the transfer function between the output variable and the input variable, G, is simply given by a 0 in the right half plane. So it's in the right half plane. So it's 1 minus give you that, say, the plane in which light is 0, S over omega zeta, which is the 0 pulsation. So at low frequency means that S is very small. Typically, we can, say, examine this situation by putting S 0. Then you have 1. So it means that the output quantities U out is equal to the input quantity, okay? If you increase the frequency, what does it mean? If you increase the frequency, S becomes larger. And so, extremizing this reasoning, if S is very large, it's going to infinite, the ratio between S and omega zeta is larger than 1. So you can get that at the end, you can have this. At the end, when frequency is very large, then you can have this kind of sign. So that means that you have a negative sign here. So because U out over U in now is negative S over omega zeta for very large frequency. So you have a phase reversal. The phase of your system is changing from positive at low frequency here, okay, to negative at very high frequency. This happens, so you have a phase reversal from positive to negative, and this happens in, say, of course, frequency domain. But if you look at the implication in the time domain, so you can have, let's say, the transient response, this means that the quantity U out, when you have a variation in the input, and if you look in the time domain, instead of, say following the U in variable, so changing U in positive means that U out should be increased, that when you have this step change in the input variable U in, initially the variation of the output is, let's say, in the wrong direction. It means that instead of increasing U out against the input variation, step input variation of in, then initially, following the input step, the output quantity U out decreases. And then only after a certain time interval, it can increases again. So you have a phase reversal in this sense. Of course, this happens exactly when you have the step at the input, okay? When you have, say, enough time, then you get in, say, steady state, so DC, and then at the end, you can get the same quantity as the input. But initially, when you have the variation, when you have the disturbances, the output quantities goes in the wrong direction. Of course, in terms of stability, this is something which is bad, because suppose that you have a boost, okay? And that boost, you have your steady state condition. But at a certain point, what happens is that you have a variation in your example, say, duty cycle. And the variation of duty cycle is in the sense that you want, for example, to increase the output voltage. Okay? So what happens is that initially the output voltage, instead of increasing, decrease. So it's going to the wrong direction. I want to say this example about the boost. I want to say describe in a better way. Okay, so because it's very important. So let me share this whiteboard and consider what happens in a boost. Okay, so let me redraw the circuits. Of the boost, which is made by an inductor, a switch, a diode. Okay, I want to control the output voltage. Okay, my output voltage should remain constant for variation of, let's say, the several parameters. But suppose that at a certain, so for example, suppose that we are in steady state and look at the diode current. The diode current is the same of the inductor current when the switch is off, so during the off. So the inductor current is something like this. We are in CCM, so the current has this behavior. This is, sorry, this is TS. Etc., etc. Okay, 2TS, 3TS, etc. Okay, remember that the average value of the current through the diode is the I0 current. Supposing that this is the average value. Okay, so at a certain time instant, some disturbances make the output voltage to be lower than the nominal voltage. Okay, so at certain time instant, suppose that for some reasons, I want to investigate, V0 T decreases. Remember that V0 is equal to V in 1 over 1 minus D in CCM. So if you want to increase V0, okay, if you want to increase V0, you have to, let's say, enlarge the duty cycle. Okay, you have to enlarge the duty cycle. So solution, the control increases D. Okay, this simply stated. Okay, so V0 decreases for some reason. The control that senses the output voltage recognizes that the output voltage is less than the reference voltage. So some action should be defined, and this action is to immediately increase the duty cycle. Okay, so the duty cycle in the switch should be increased in order to, say, have again the same nominal output voltage. What does it mean increasing the duty cycle? Increasing the duty cycle, okay, here you have T on. So increasing the duty cycle means that you, and T on is D, yes. So it means that you are increasing T on. So suppose that this happens in this cycle, okay? So here, the duty cycle has a step, D plus, say, the hat, because I want to, say, have the same output voltage. So the control command, what happens that my T on should be larger. But if T1 should be larger, it means that my current step in the diode starts a little bit later. For example, start here. Okay, because I have to enlarge T1 prime, which is larger than T1. And so this step starts later. What does it mean that this diode has a current that, say, the diode becomes on later with respect to the previous cycle? What happens during T-on? During T-on, we have the switch which is on, the diode is off. So during T-on, the circuit is something like this. Okay, this is during T-on, the diode is off. We are in this region here, okay? So in that situation, how can the output voltage can be maintained to be constant? By the charges, by the voltage across the capacitor. Since my hypothesis that the time constant of reactive elements are well higher, larger than Ts, I can say that this capacitor cannot be discharged during T-on because its time constant is too large with respect to Ts. So if this hypothesis is good enough, so I can say that, okay, C0, the voltage across C0 and the energy which is stored into this capacitor is able to maintain V0 constant during this phase. Okay, but look at what happens after this step in the duty cycle. My T-on is enlarged. So it means there is a time interval in which the diode is off, which is larger than the time interval in which D is off in the previous cycle. Okay, is larger. Now the current starts later to be conducted by the diode. So this capacitor should be maintain the output voltage at the same level for a larger time. But you have to understand that even if this capacitor has a time constant which is larger, then it means that it a little bit should be discharged with respect to the previous cycle. So the output voltage during this time interval here, in which the diode is not still on, the output voltage is a little bit less than the output voltage you get in the previous cycle. So it means that you look at the plot of the output voltage. The output voltage, for example, is, let's say, a certain value here. But then when we have the duty cycle variation, the output voltage goes down. But remember, my intent is to increase the duty cycle to increase the output voltage. What is the result? That the output voltage is not increasing, is decreasing. Then it happens that after several cycles, okay, the output voltage increases again and goes to the right direction. But to have a certain time interval following the input step at the duty cycle, commanding the duty cycle to be larger, in which the output voltage is decreasing due to the fact that the energy in the capacitor is not large enough. It will be discharged a little bit more than previous cycles, since T-on is larger. Okay, so in the next cycle, it happens that not only there is this delay, but only the input, say, the current increases a little bit, so the energy here, so the output value of the current increases, and then the output voltage increases. But anyway, there is a momentary time interval in which the output voltage goes in the wrong direction, exactly like in the simple system I showed you before. Okay. And this is always a sign that the system has a right half plane zero. This is the reason why it's not so easily to control in CCM a boost. Okay, I want a system in which when I command the duty cycle to be larger because I want, for example, to increase the output voltage, then immediately this is happen. Not say after several cycles, because otherwise what is connected to the output port of the boost, the load, it could be say could be fails, could be, say, you have damages, I don't know, something that is not admissible. Okay, so this is basically what is written in this slide. Okay, but this example is for duty cycle 0.4. They change it to 0.6, and that means that, let's say, you have this kind of delay in turn on the diode. That means that the capacitor should withstand the same voltage for a longer time, so it will be discharged. Okay. If you have questions about this right half plane 0, the same happens for the buck boost. The buck boost has a diode in the same position. Okay, is reverse, say, polarized, so the cathode and the anode are exchanged, but basically the same happens for the buck boost. Okay, so even for the buck boost, say DCM is a better way to control it, because in DCM they do not have this kind of problem. Okay, we see what happens in DCM later. Okay, so as you can see, switch mode state space averaging techniques can, say, bring us to the right solution, but we have to do a lot of mathematics. Okay, maybe it's not difficult, but okay, it's something that you have to do. And then I have just considered something very simple. The elements that are not have parasitics, all are ideal, etc. If you put something which is not ideal, of course the equations are just more complicated. Just to give you an example, if you want to put the equivalent series resistance in series with output capacitor C naught into the analysis, then we have to, say, multiply the equations, because not only I need the state variable equation like that I written before, but pay attention now, the voltage, the state variable VC naught is not the output voltage. So previously I have some, say, simplification, because I said, okay, VC naught, the state variable voltage across the capacitor, is the same, is equal to the output voltage. But now this not happens. So in the first equation, you have to write down exactly the equations taking into account VC naught. And then I need another equation, which is this, say, output equation, in which I have to explicitly indicate the relationship that there is between VC naught and the output voltage. Okay, VC naught is V naught is VC naught plus the voltage across this resistance. And this is written in this equation here. Of course, I don't want to, say, explicitly and put all the steps here, because the equation, even with this very light little modification, will be complicated. It's easier to, say, to lose some terms and to get in the wrong direction. Okay, I give you the result. The result is this one. Okay, if you put that ESR in the output equation and you solve the equation, you get something which is like this. This is the control to output transfer function. So V naught hat versus the variation of the control duty cycle when the input voltage is considered to not vary. And this has this expression. As you can see, it's very similar to the previous one, because we have the right half plane 0, then we have again 2 conjugate poles. But now there is a contribution of the ESR, and this contribution manifests itself by another 0, but now this is a good 0 because there is a plus here. 1 plus S C naught ESR. And then ESR appears even in, say, multiplying the coefficient of S squared and S, or summing up here. Okay, so in this equation we can make some, say, practical situation hypothesis that ESR, which is a parasitic resistance, typically is much lower than the load. Okay, and also typically this time constant can be, say, have these inequalities. Okay, the time constant of AL and the load is much higher than the time constants of C naught ESR, because its ESR is very, very small. So we can skip this quantity is equal to 1, and this is equal to, let's say, negligible. So this is almost null, and this is again almost null. So my numerator is the same as before. There is no changes at all. Of course, in approximation, but this happened. While the numerator has this other pole, and the pole has this frequency. Okay, 1 over 2p C naught ESR. Okay, is the pole of this network here. Sorry, the pole. Is at 0. Okay, 0 is a left half plane 0. 0 due to that ESR. And so this is my final expression for the boost CCM. You have one right half plane 0, one left half plane 0 due to the ESR of the C0 capacitor, two complex conjugate pole. The 0, the right half plane 0 is moving 0, so changes depending on the condition R and D. The complex conjugate pole are moving poles. The left half plane 0 due to the ESR is fixed, only depend on ESR and C0. It's not moving depending on the condition. Okay? So we derive this contour out function for the boost CCM, explaining also the origin of the 0 in the right half plane. If you have questions, I'm here to answer your questions. Next time we move to another method, and we employ this method to derive another transfer function for another converter. Okay, guys, thank you for your attention. Okay, questions. Cannone Marco. ESR fix the problem? No, absolutely not. They are two different zeros. They are not one. Even if you are one on top of another, the phase is, let's say, different. You cannot have the same, say, you cannot cancel out one with the other one. Okay, this is not possible. The right half plane 0 remains it here, and this is due to the qualitatively I express my defect by using this reasoning. This reasoning has nothing to do with ESR. Even with ESR in the output capacitor, you can say the same. Also, maybe it's worse because now we have a time constant which is less, so the output capacitor can discharge, say, more easily due to the ESR. Okay. So if you look at this explanation, I said nothing about the fact that C0 has or not have not has this ESR. Okay, it's equal the explanation. Okay. Other questions?